Well, hello everyone. I wanted to make a movie that focused entirely on this idea that is so profound and powerful, namely the distribution property. This is an axiom, that is to say, it's assumed to be true. It's not proven. That runs through every math course you'll ever deal with, from here through college algebra, statistics, and calculus. It is a major deal and is leveraged in so many different ways to simplify situations. Now, the way it's normally described in a textbook is like this, which is perfectly fine if you are happy interpreting symbols and algebra. But for many of you, you're a bit shaky in math, and I thought what we'd do is we'd figure out a way to uh, swallow this thing and master it in as deep a way as possible. In other words, what I'm looking for here is for the overarching thought for mastery. And I think I found it in the simplest English possible. Namely, here it is. Every bit of one number has to multiply every bit of the other number. That is the essence of the distribution property. Now, here you see an example. I have all of 3 multiplying all of 5, and of course that gives me 15. So a nice place to start. Everybody's familiar with 3 times 5 is equal to 15, but let me complicate that and move it into algebra and show you how I leverage the distribution property. What I've done here is rewritten the 5, broken it up into 2 bits. 3 plus 2 is indeed 5, and 3 times 5 is still going to give us 15. Now, according to the order of operations, you always do what's inside parentheses first. But the power of the distribution property is it actually allows you to short circuit the order of operations and to literally leap over these parentheses, do an end around these parentheses with this multiplication. So what you're going to get here is all of 3 multiplying both bits of 5. So you're going to have 3 times 3 or 9, and 3 times plus 2, which is plus 6. So you're going to have 9 plus 6. You're going to have this, which of course sums to 15. So I've broken 5 up into 2 bits, and this is single distribution, and it makes good sense. Essentially, we've ignored this addition and went ahead and did the multiplication. But I could just as easily break 5 up into more bits, and that's what my next example shows. Here I still have 3 times 5, because look, 10 minus 3 is 7, and 7 minus 2 is 5. I've just broken 5 up into 3 bits, and the idea is to show you is that all of 3 has to multiply all of 5. There's going to be 3 multiplications here, if you will, or 3 arrows. And what we'll get is 30 minus 9 minus 6. 30 minus 9 minus 6. Of course, 30 minus 9 is 21, and 21 minus 6 is 15, and so it works. It's really powerful and very almost magical. And I'm only going to show you how much more magical it can be. So far, I've left the 3 untouched. I haven't broken it up into bits. But I could do that like this. I've broken the 3 up into 2 plus 1, and I've broken the 5 up into 3 plus 2. Now, technically, we're looking at 2 binomials in algebra speak, and we would use what's often called in, well, probably every classroom in high school math, it's called FOIL. And basically, it's a legitimate idea, but it's an oversimplification. And in a sense, it's sort of like a crutch. And really what's going on here is double distribution. It's just the distribution property. You don't really need to ever mess around and learn FOIL. Basically, all you have to know is that every bit of 3 has to multiply every bit of 5. Now I want to bring in the drawing program and show that with arrows. So here we go. And what we're going to do here is pick up the pen, and I want to show you that every bit of 3 is going to multiply every bit of 5. This first bit has to multiply both of these bits, and so we're going to get 2 arrows. And when we do that multiplication, we get 2 times 3 or 6, and then we get 2 times plus 2 or plus 4. Now every bit of 3 has to multiply every bit of 5, so this bit has got to multiply both of these. And we're going to have 2 more arrows. And so we're going to have 3 plus 2. And please note that this does indeed equal 15. And so double distribution works, single distribution works. It's a universal axiom that is true everywhere and everywhen. And once you know this idea right here, every bit of one number multiplies every bit of the other number, you no longer need FOIL, which is just a special case and teaches you that order matters when it really doesn't. What I'm saying there is that, believe it or not, FOIL works just as well if you call it LOIF or OILF or any other permutation you can think of those 4 letters. It's going to work just as well. Let me bring in the drawing program again and show you that, because I know all of you have dealt with this FOIL before and you're very much wedded to it and you don't want to let it go, and that's fine. I don't want to force it away from you, but it is in a sense a crutch, and if you can get past it, you can take a great leap at mastery. So I want to do this. Remember, every bit of 5 has to multiply every bit of 3, or vice versa. And it doesn't matter where you begin or where you end, because the order of multiplication doesn't matter. 3 times 5 is the same as 5 times 3. So I'm going to do the last here first. That's the last. That would be these two, and that would give me a 2. In other words, I'm multiplying like this. And now I'm going to do the outsides. These are considered the outsides of 2, and so I'm going to multiply these two, and that gives me a plus 4. And now I'm going to do the insides, and so now we're talking about this bit of 3. This is the insides of the 2 binomials, and I get a 3 there. And now we're going to do the first. In other words, the first term here and the first term here, this all right here, and that gives me a plus 6. And of course you could sum those up and you're still going to get 15. So you see what I mean about FOIL? It is, in a sense, it's just a small vision of the total truth, which is every bit of one number has to multiply every bit of the other number. Now I want to finish this up here. Let me create some space and drag in something here. I want to show you a more complicated situation that FOIL could never get at, but this thinking does with ease. Here is an example of a binomial times a trinomial. Now, make no mistake, this is still 3 times 5. This is still going to equal 15. 10 minus 3 is 7. 7 minus 2 is 5. This is just 5, and this is just 3. And I want to show you that every bit of 3 has to multiply every bit of 5 here. Let's bring in the drawing program. And really what I want you to think about here is how many arrows are there going to be. And so when we go to this first bit, we're going to have, I think you see, there's going to have to be 3 arrows. Because every bit of that 3 has to multiply all 3 bits here. And similarly, there's going to be 3 arrows here. Now when we do all these multiplications, there's going to be 6 of them. We ought to get 15. Let's see, we're going to get 20 minus 6 minus 4. 20 minus 6 minus 4. And then we're multiplying all of these 3 terms by 1, so they're not going to change. And we're really just going to get 10 minus 3 minus 2. And of course the 10 is positive. 10 minus 3 minus 2. 20, this is a 10, and this is a 10. 20 minus 10 is 10, and 10 plus 10 is 20. And so we have 20 minus 3 minus 2, or 20 minus 5, or 15. And so you can see I multiplied a binomial by a trinomial, and I simply use this piece of thinking right here. Every bit of one number has to multiply every bit of the other number. That's this distribution property. Okay, last move, last thing. I wanted to show this idea totally fleshed out. In other words, what I'm going to do here, and this might seem crazy to you, but it really illustrates the point, is break up 3 and 5 into their maximum bits, so to speak. Notice I've just using all ones here. 1 plus 1 is 3. 1 plus 1 plus 1 is 3. And of course I have 5 ones here, so this is 5. This is really 3 times 5. And I want to ask you, how many arrows, how many multiplication arrows are they going to get when you multiply every bit of 3 by every bit of 5? Let's bring in the drawing program. And you've thought about that for a bit. I think you know what's going to happen here. There's going to be 5 arrows from this first one to all 5 of these bits, right? and then there's going to be 5 arrows from this one to all of those 5 bits. And then there's going to be another 5 arrows from this one to all of these bits. And so all told, there's going to be 5 arrows, 5 arrows, 5 arrows. There's going to be 15 arrows. Yeah, 15 multiplications. And every one of those multiplications is 1 times 1, or plus 1. And so really what you're going to get here is this. 15 ones, like that. And of course, 15 ones is simply 15. And so the distribution works. Extraordinarily powerful property. Now I'm going to follow this video up with another one that's going to take this, it's going to leap the idea ahead into the final chapter before the midterm. And I hope you watch that one too. Be talking to you soon.